Hello, everybody, and welcome to today's webinar from Hydromantis. We're going to be talking today about modeling energy usage at water resource recovery facilities with our GPSX modeling package. So this is one of our ongoing series of public webinars that we provide so that users and modelers and interested people can come and find out more about getting the most out of GPSX and about some of the more advanced features and techniques and details of our software. My name is Spencer Snolling. I'm VP of Product Development here at Hydromantis, and I'm glad that you could join us today. Our plan is pretty much similar to what we've done usually, which is that I will spend some time with some PowerPoint slides going over some details of our modeling package. The plan is that I'm going to talk about operating cost models today, and specifically we're going to stick to the part about modeling energy usage. So I'm going to talk about how we calculate the amount of energy that is required to supply air and oxygen to the activated sludge systems. I'm going to talk about the pumping energy model, where we pump actually any of the liquids around the plant, most significantly the recycled activated sludge and so on. And then I'll hit on a few other highlights of other small sources of energy usage that you can incorporate into your model. I'm also going to discuss our anaerobic digester model today because it includes a portion of that model that is used for modeling energy recovery. So we can talk about biogas production and burning methane and getting some energy back from that, and how that is part of the model that you have available to you. And as part of that, like we always do, I have 3 separate desktop demonstrations that I'll be doing today, jumping back and forth between my slides and copies of GPSX, where we're going to run some simulations live. And as always, we will be answering questions live at the end of the webinar today. So in your GoToWebinar dashboard, you will see a questions panel. You can go in there and type questions. I'll accumulate those. Just type them at any point along the way during the presentation. And then about 30 minutes from now, when we get to the end, I will take some time to answer as many of those as we can. All right, on with the webinar. So basically, I wanted to put together a webinar here to highlight some of the very simple energy calculations that are available to you as part of GPSX. These are things that are already built into the software. You don't really need to do anything special when you're putting together your wastewater treatment plant model. When you're drawing out your model on the drawing board and you're dragging those tanks and clarifiers and other objects onto the screen and hooking them up, the operating cost models are already there. They're all built in into the background of the system. So we're going to talk a little bit about the stuff that is specific to each individual unit process, and then we do some overall calculations for the whole plant as well. So any object that has a pump connection point has stuff built in. Anything that has aeration has one of these operating cost models built in. And then anything that has any sort of other kinds of energy consumption, so for, say, moving rakes in the secondary clarifier and that sort of thing. So those will all be there. In one way or another, we will allow you to specify some energy usage or calculate it for you, and that can go into our overall evaluation of the consumption of energy for the whole plant. Okay, so on a unit-by-unit process basis, all of the input parameters that you're looking for with respect to energy are found in the operating cost menu. So you right-click on your activated sludge tank, go to Input Parameters, go to Operating Cost, and then you will see a menu that looks like this. It has on it details that are different depending on which object that you've entered. But so, for example, a completely mixed activated sludge tank, you'll see the details for the blower and the aeration system, and a combined efficiency and so on, and the details about how much head we're pumping against. And because this is a completely mixed tank, we have a mixing power and other things too that you can take advantage of. We have some default values put in there for you already. You can turn those off or do whatever you like. I'll come back and talk a little bit more about how we calculate all that stuff. So once you've entered in all of that information, you can then get the output from that, just like you can any other typical variable in GPSX, by going to that object, right-clicking on the object, go to the output variables menu and down to operating costs, and then you'll see details both of the energy usage itself. So you'll see the instantaneous power that is being required to deliver that aeration. And then you'll also see the amount of energy that is required because we're accumulating that over time. So power in units of kilowatts, and then we're integrating that over time, which gives us kilowatt hours for the amount of energy that's been used. And as I'm going to show you a little later on, we also are multiplying that by the current price of energy at that particular instant in time, and then we integrate those dollars as well. So you can get both the energy or power numbers off of this menu and also the dollars off of this menu as well. So all of that will be there. This particular menu will again look a little bit different depending on which object that you have right-clicked on. Sometimes it'll be longer or shorter depending on whether there's aeration or not in that object. So you'll find that by going to that output variables operating cost menu and working from there. Okay, so now I have a few slides that I'm going to talk about how we calculate some of those numbers. And I'm going to breeze through this pretty quickly because this is actually, we could spend a whole half a day, and in fact I've done that with many of our GPSX training sessions, is to spend a full day or half a day on how we calculate this and go through some exercises. I will refer you to our technical reference guide for GPSX for all of the really super detailed information, but just to give you a summary for the kind of information that we use to calculate it, I'll show you a few equations here. So in the case of wanting to calculate the instantaneous requirement for energy for a pump running at a particular flow rate, we then use this equation here. It's a very simple, very straightforward one that makes some assumptions about linearity, of efficiency, and a few things. We have more complex ways of doing this at the very end of the webinar. I'll touch on those. But right now, this is the simple approach that we have available in all of the objects, where we take the flow rate times the head of water that we're pumping against times the density of water, and then we divide that by an overall pump efficiency, which, you know, generally we have some default values of 0.6 and 0.7, 70%. And so that energy then is calculated and then is used, integrated over time and multiplied by the energy price and so on. So these are very simple, straightforward. Any place that you see a pump connection symbol on a connection in a GPSX object, you will find the ability to associate this type of energy usage, and this will be available to you in the menu. We also do it for the internal recycles for our plug flow tanks. If you're setting up a BNR system and you're recycling flow from the end of the plug flow tank back to the beginning or to somewhere in the middle, those rates as well, you can set a separate head for those and a separate pump efficiency, and that will be also calculated in as well. So those things are there, and that kind of system is being used for us to get there for pumping the water itself. Now, for the aeration system, we're doing a very similar kind of thing, although there's a lot more options with our aeration calculation. First of all, there's the difference between mechanical surface aerators and the diffused aerators. So in mechanical surface aeration, you are specifying the energy input already anyway. So right now we're asking you to enter in the horsepower or the kilowatt hours. So no conversion required. We just take that number and then that's added into all of our calculations. For diffused aeration, it's a different system though. We need to calculate what that energy requirement is. What is that instantaneous power from the airflow rate that you are specifying? And in that case, there's quite a lot of things that come into consideration here. The air temperature, the flow rate, the pressures at the inlet and the outlet, the pressure loss, diffuser submergence, and the head loss, and so on. So all of these items are going to be either estimated from other parts of the model, or we will ask you for that information on the menu. And so all of that information is collected up, and we perform this calculation to get an estimate of what's going on for a particular flow rate. So now we're off and we've got our power. We can continue on the way that we did before. So I'll reference you over to our GPSX technical reference guide, page 385, if you want to look into this in even more detail than what we have displayed here on this slide. So we now have, for pumping and for aeration, the instantaneous power that is required in order to deliver that pumping or blower. And then what we're doing is we're integrating that over time to get kilowatt hours, then we're multiplying by that to get price. So all of that information is available for you on the system here. Key thing to remember is that we're talking about instantaneous calculations for power. So when we integrate them over time, as the load changes and as the flow going through the plant changes, we are going to integrate that over time. So we can reflect the dynamic changes, and one of my examples that I'll show you here today does do that. When we are calculating the cost, we are also doing that on an instantaneous basis. So I know that as I'm producing, or as I'm requiring a certain amount of energy to be used, I know that at that particular time the price is a certain amount. Then the next amount of dollars that I add to the pile that is going to be integrated over time, is done at that price at that particular point of the day. Now, since our prices can go up and down during the day, that's a really useful feature because we can show how energy used at a time when the price is cheap does not accumulate as much cost as using the energy when the time is expensive. Okay, so I'll show you in a moment here about how we adjust the price. When you're plotting all of this information, I just showed you this graph here, and you want to be able to plot how things change over time. These are just like any other variable that you get off of any one of our output variables menus. And so you can do that for any of the graphs that we have. So, but the other key interesting feature is that we've now gone around, for any model that you build, gone around to all of the objects and added up all of the different kinds of energy requirements and give you an overall total for the entire wastewater treatment plant. The way you get that information, if you want to plot that, is to right-click on an open point in your drawing board, so a blank spot on your drawing board. Right-click, go to Output Variables and Operating Cost, and now you have the menu for the entire plant. It includes actually all of the operating cost calculations for all of the objects that we have. So here you can see that it shows you the total power cost for all of the objects together, for the total cumulative cost, the amount of power that's being used. We're doing it per day, and then the amount since the beginning of the simulation. We can break down our energy usage. There's a few other things on here outside of energy as well, such as the total chemical cost, and then a total cost for the whole plant. So this is all interesting information that you can collect off of here and plot on a time series graph, or put it in a table, or export it out to a report, whatever is your favorite way of displaying information in GPSX. We certainly have a lot of different ways that you can plot and view the output from the model. And these variables are there for you to add to your list. So alongside your performance variables and looking at effluent quality and mixed liquor concentration and sludge production, you can plot energy requirement, and you can plot chemical dosage and other things too. Lastly, this is a relatively new feature in GPSX. I say relatively, we've had it for a couple of years now, is the plant-wide energy usage summary. It's one of the buttons that is along the top row on the right-hand side when you're in simulation mode. And it's supposed to look like an electrical plug. So this is, you click on that button, and then what it does is it draws out an image of your plant, and then it highlights different kinds of energy usage by putting boxes of different colors around the different unit processes that you have. So in this particular example, I'm looking at aeration power. So there's a certain portion of those activated sludge tanks that are using aeration. So we can see here that we're currently using 30.79 kilowatts to run this particular system at steady state. So you can break it down and look at it in various ways. We can assemble that same information as a table for all of the objects, or as a pie chart. And I'm just going to show you in a minute here how to get into some more details there. Okay, so that's a lot of talking. Let's get on with doing some actual modeling here. So I'm going to jump over to my copy of GPSX. So for this first demonstration, I just want to show you where the information is, what it looks like, and we'll plot a very simple simulation. We have some flow coming into this simple activated sludge unit with completely mixed aerobic reactor there. So let's come over here, and I'm going to run a 2-day dynamic simulation. I have steady state check, which means we'll solve for steady state first, then we'll run 2 days, and I have the flow coming into the plant set to do a diurnal pattern. So let's just run that quickly. That diurnal pattern is shown here. What you can see is this is the amount of power required to do the aeration system as it goes through 2 days. So you can see during a day, it goes up and down as the load itself goes up and down. Now we kept the concentrations the same, but the amount of flow coming into the plant goes up and down. And the aeration requirement obviously goes with it. As we have more loading, the DO controller in that aeration tank is holding the DO at 2 milligrams per liter, and therefore it's turning up the airflow when it needs to treat more load of BOD and ammonia, and therefore we can see the energy draw to be able to do that. We're also, just for the sake of illustration here, we're also accumulating and seeing what is the total amount of energy that has been required since the beginning of the simulation. That's what this red line is. So obviously it's 0 at the beginning, and by the time we got to the end, we're showing here that we've accumulated 12 kilowatt hours, or sorry, that's times 10 to the minus 3. So we've accumulated a certain amount of kilowatt hours for those couple of days. Okay, I'm going to move over to my costing tab here. This is an example where we are having the cost of the energy change during the day. So this is 2 days again, and we can see here it starts at midnight and the price is low, and then it comes to a certain point in the morning where it jumps up to the higher price, stays there for a while, and then in the evening it goes back to the lower price overnight again, and then back up the next morning. So this is a case where those prices change during the day, and we can see that the amount of energy we spent was $1,112. So that's what it costs to aerate this particular system. By the way, this is about a 10 MGD plant. To do about a little over $1,000, $1,100 worth of energy required to fully aerate this particular system. And just for the sake of it, also there's our effluent product, our effluent quality. So we can see that it's fine, it's fully nitrifying, and our effluent solids, they're a little higher during the peak loading time. And they're quite low during the middle of the night, and that would be normal, what you would expect for a diurnal pattern such as this. Okay, so that gives us a feeling for where all of that kind of information is what it looks like when you're using it. We can actually click on any one of these particular units here and go to that operating cost menu, and we can dig into further details here about how much of that information was used for all of the various elements of this particular simulation. When you're doing it for a clarifier, I'll note that you have to go to the overflow connection point, then click on output variables, then get to operating cost, and you can find all of the details in this particular case for the pumping energy and so on. Okay, I wanted to show you now the overall usage plant-wide summary. However, this plant's actually not that interesting to look at because it's only got 3 objects. So what I'm going to do is I'm going to flip to something that's a little more detailed, so we can take advantage of that. So what I've done here actually is I'm going to select one of our layouts that is available in our sample layouts menu. So in our sample layouts menu, we have lots of pre-built plants that do a lot of different things. And in the software features side, we have an energy example. And here we have a plant that's actually 2 plants in parallel, and we have some, activated sludge system already put together here with some recycles. We have some chemical dosage. We have another object over here that's using a bit of energy. So let's just run this at steady state, and then we can take a look at the details of this particular system. So in this case, this plant is fully nitrifying and denitrifying, and it's doing some chemical phosphorus removal as well. So now, once that's reached steady state, I can click on this button, and we can see the overall plant and the overall summary of the energy usage. Right now, we're only looking at aeration power, which is why it's only associated with these 2 objects. They're the only ones doing aeration. I can switch to pumping, and we can see here In this particular example, we have a lot of energy usage associated with the RAS that's going back to the head of the aeration system. We even have a bit of pumping associated with the internal recycle here. We have quite a bit of flow and energy usage with our influence, so that would be an example where you might have to, as we do here in Hamilton, Ontario, lift the flow coming into the plant quite a lot because it comes in at about 70 meters below ground. Or something along that nature. You can also go over to the table pie view here as well, and you can click on individual units to get those details. And then we can also click on the entire layout and get a summary for the whole plant. So this table, this pie chart are all available for you to take advantage of and to export out to your spreadsheets in terms of tables, or to use these graphics and export them out from these buttons up here to include in your reports. Okay, so let me go back to the slides now. Okay, so we talked about how we calculate the power requirement and how we've accumulated both the energy usage and the dollars. What I haven't talked about yet is how you set the energy price. So the energy price can either be a constant during the full length of the simulation, or it can fluctuate during the day or the week or the year. And the way that you get to those settings is, again, right-click in an open spot of your drawing board, select System, Input Parameters, and Operating Cost Settings, and you'll come to actually a very long and detailed menu, which I had to divide into 3 parts to put on my slides here. That controls how you change the price over time. So there are 3 options at the very top of the menu. You can either have a constant price, you can base it on time during the day, or you can base it on season on top of that as well. So I'll just quickly show you what some of these options look like. A constant price is pretty straightforward. This is our default value of 10 cents per kilowatt hour. It means that value just stays the same throughout the simulation, unless you choose it. I mean, it's like any other variable. You could put it on a slider, move it around. You could read it from a file, whatever you like, but otherwise it will stay constant. If you select the time-based pricing, you can choose that there are different zones of time during the day in which you would have a different energy price for each one of those times of day. So we do that here by selecting, by default here, at 2 price levels, so day and night. And we have different energy prices where we would have cheaper energy at night and more expensive energy during the day. For example, you specify those prices here, and then you use what hour of the day that it switches to the next price. And you put those into that information there. And lastly is our full-on season and energy pricing, which is the most sophisticated way to set the price. There's actually, first of all, by month during the year. So there's sort of summer pricing and winter pricing. And then we have, within a particular day, we have times that it is more expensive than others. And we have 3 prices here: off-peak, mid-peak, and on-peak pricing. And then we have weekend and weekday costs, and we can set up an entire system here to actually in a very sophisticated way control how that price changes over the year. So that's available for you to take advantage of. By default, it's just going to keep it constant, but you can come in here and activate one of these other operations as well. Okay, so what I'm going to do is I'll go back to GPSX now, and I'm going to demonstrate, for example, how that works with a dynamic simulation where things are changing during the day and the price of energy is changing during the day. So I am going to go back to a very similar model to what I showed you before. This one's got a couple of more elements to it. So it's roughly the same size of plant. We do have our daily diurnal pattern on the flow coming in. However, we have an equalization tank ahead of the activated sludge unit. So in this case, I'm using this equalization tank to hold back some of the flow during the period of time when the energy cost is high, and then pump back that flow and add to the flow during the time when it's low. So we'll sort of optimize our energy usage. It's a completely hypothetical situation, but I'll show you how you could set that up here in this layout. I am going to take advantage of our scheduler controller, which is found in the process control group over here. What it does is it basically just controls the flow rate at which this pump is on or off. And it basically repeats the same pattern over day after day after day. And I've got that all lined up now, so that what it'll do is when the time changes from the expensive energy to the cheaper energy, that's the time when I want it to pump a little more. And when it goes to the expensive energy, I want it to actually hold back and fill up this tank a little bit until it gets to the next cheap time, in which we'll empty the tank back out again. So the tank's going to start empty at the beginning of the simulation. Okay, so we're going to run 2 days again. You'll be looking at a very similar graph as what I showed you before. So there's 2 days, and we can see here's our flow going up and down during the day. So we can see our aeration requirement in terms of power is going up and down during the day. And let's take a look at the cost. Right now, this red line represents the amount of flow that is coming out of that equalization tank. It's basically the same. The influent is just flowing straight through and into the aeration basin. So, and here's our energy going up and down during the day. This is the uncontrolled version. It's the same thing that I showed you before. As you remember, it's around $1,100 to aerate for 2 days. Okay, so now I'm going to turn on the scheduler. So what will happen is we'll now see that some of that flow is going to be diverted. So I'll explain this set of lines down here. The black line represents the influent flow to the plant, as we would have seen before. And you can see here that the red line represents the flow that's coming out of the equalization basin, now that our controller has a handle on it and our controller is controlling how much is going in and out. So right now, even though the flow into the plant is a higher value, we're actually not pumping all of it over to the aeration yet. We're actually holding back some of that volume in this tank. And you can see here, this blue line represents the volume of liquid that's being held back in that tank. So at the beginning of the simulation, it was empty. And then once we started to sort of hold things back, it starts filling up again. And then at the point when here the energy cost goes from being more expensive to less expensive, now is the time when we want to turn on that pump and ramp it up a little bit so that we can empty that tank out at a time when it's cheapest to do it. So you'll note that the difference between these two lines is the volume that we stored. Essentially, we're just taking that and moving it over here and doing it during a time when the energy is less. So we pumped all that stuff out. You can see the volume returns to 0, and we were doing that at a very high level. And then we did it pretty quickly, to be honest. And then it's empty again, and then we repeat starting over again the next day. So all we were doing really is holding back this amount of flow, the difference, that little area between these two lines here, and then we're pushing it over onto the time when the energy was cheaper. So let's go look at our total accumulated dollars. You remember before, it was almost 1,100. It was like 1093, I think. And then now it's 1,016. So I worked that out ahead of time. It's about a 7% savings by pushing that amount of flow over into the time when it was cheaper. So again, hypothetical example, but it kind of shows you the really interesting things that you can do with GPSX by playing around with the timing of how things happen during the day. So let's take a look at the effluent. Now, I'm going to turn this off and rerun it again. So let me run this again. This is our normal situation, and we have some solid concentrations going up and down during the day. And we can see here that that was sort of basically what we saw the first time around. Now, if I turn on that control so that we're holding back that flow, especially during this time right here, you can see that when we do ramp up that flow and push all that held back flow through the plant at the time when the energy is cheap, it has a huge effect on the effluent solids, right? They jump up here by 50%. So now they're only going from 8 up to 13 or something. So not ridiculous, but you know, maybe that's something that would not be appropriate. Maybe it's not, the operators are not comfortable with that. So here's where the modeling comes into effect, and would be really interesting is you can go back and play with the flow rates that are in this controller and say, well, maybe we can't quite hold back that much. Let's hold back a little bit less. And you can balance off this effluent quality versus the cost that it's calculating the other day. And that's where modeling is really fascinating. You get to try and do that optimization between those two elements of your simulation here all together in the one modeling run. Okay, so back to the slides to cover off a couple of things. I wanted to talk about energy recovery. So in this case, the place that you're going to find all the energy recovery options is in the digester. So here we have a supplemental model that kind of fits onto our existing biological model that predicts our gas production. If you go and right-click on the digester, go to Input Parameters, go to Energy Recovery Options, you'll find the input menu here that shows you the details of what you can put for your energy recovery technology. So we can have a boiler. We can put some of the gas flow towards that boiler in order to, heat up the water, or and otherwise maintain the heat of that digester, supplement the heat of that digester. We can put some of that methane flow over to a combined heat and power unit to try and recover the energy directly. And there's some settings for the efficiency of doing those sorts of things as well. So once you've specified that and you run your simulation, you get some gas production, those calculations are taken care of, and we can produce some generation of potential energy from capturing those systems, both for the heat. We figure out the heat deficit, how much was required to, what is the deficit between what we're capturing and sending back into the system in terms of heat, and what is required in order to do that biological system. So kind of moving in between, or moving towards, trying to make an energy neutral unit there. And this potential fuel saving comes from one of the other settings that we have, where you would have selected what fuel you were using for this, and we can calculate how much fuel you're saving by the heat that you're sending back. And if you're using a CHP unit and you're actually generating the gas itself and generating electricity, you can actually figure out and do an estimate of how much that would be right here as well. So one thing I'll do is just really quickly show you what that looks like here. So I'm going to go to my third and final desktop demonstration here. Demo number 3, and in this case, just for a bit of variability, I am using our greenhouse gas library. This is Mantis 3 model, biological model. Our regular default model that you use when you open up GPSX is Mantis 2. Mantis 3 is the same thing, plus we also have our greenhouse gases in there as well, a couple of other extra details in the biological model to support that, and our carbon footprint library. So now the actual thing that I was just talking about in terms of digester energy recovery, it is available actually in all of our libraries. Like, it's available in Mantis 2 and in Mantis 3 as well. So I had just happened to be using Mantis 3 for this demonstration. Right, so let's just run a steady state solution to that model. And if I click on the digester here, we can get some results. I'm just going to open this up a little bit bigger here. We can see some VSS destruction. I'll get close to 50%, not too bad. We got some gas flow here. And if I open up the output variables and I go to, actually not the operating cost menu this time, but specifically the heat generated from methane recovery, that's a special menu where you're going to find some of those details that I mentioned before. So there's a lot of interesting things to play with. I'll refer you actually to a couple of places, again, back to our GPSX technical reference, where how all of these calculations are carried out is covered in detail. And actually, we have actually talked about this in quite a bit of detail in one of our previous webinars. So if you go to our YouTube channel and look up the greenhouse gas and carbon footprint library webinar, you'll see a lot of details there about that. Okay, so back to the slides to wind things up here. There are two other things I want to quickly mention because they are relevant to doing energy modeling. We have a couple of objects that are available in GPSX to go on your drawing board that are even sort of more extra things that you can put on to capture energy usage in more detail, in a more broad sense, or in a more sophisticated sense. One of them is our building object. You can put one or more of these buildings on your drawing board. They have no effect of any kind on the actual process. The water does not flow through them. They're there basically to represent other buildings that might be part of your wastewater treatment plant but do not contribute in any way to the process. But they're there and they're using energy. So you'll see here the details are for heating and air conditioning, lighting, and we also included some details about refrigeration here. You specify some details about how all that is being used. We look at the ambient temperature outside to see how much energy is required to heat a building in a certain location with a certain internal temperature. And then we add that energy usage into the overall calculation of energy requirements for the plant. You can put down several objects if you like. And lastly, I also mentioned our pump object. This is an inline pump object that you can put in your model anywhere that you like. It has no effect on the concentrations. It's really there, again, to just model the energy usage in more detail than we would before. So I mentioned way back at the beginning of the webinar today that this is a very simple approach that we've taken for a lot of the pumping. We've assumed a very linear relationship for and constant efficiency. If you would like to model the pumps in more detail with an actual proper pump characteristic curve and a system curve, you can do that in GPSX, but you have to put one of these objects into the system anywhere you want in the connection line as it moves from object to object. The purpose of this was it allows us to model things in quite a lot more detail. So for example, you can define the pump curve. You can define whether you're using a series of pumps in parallel and whether you have fixed speed pumps or variable speed pumps. And as the pump operation moves up and down and you're pumping different flow rates at different heads, for example, you will get different efficiencies. So, and again, I will mention that we have done a whole webinar just on this one particular slide, one particular topic. We actually have a very nice paper from, I believe, 2 years ago at WEFTEC that describes all of this in detail. Okay, so just to wind up a few things here, I've gone a little bit long. Basically, GPSX contains a very wide array of energy calculations. They're standard, they come as part of the model. You don't have to do anything extra, just put those objects on the board and those menus are there for you and the calculations are happening. The automatic energy usage summary, that electrical plug button, is a nice way to sort of organize and export all of that information. And you can use our digester to model energy recovery with any of your layouts.